So this kind of leads us to another method for basically with clustering called hierarchical agglomerative clustering. So hierarchical clustering. I can't talk. Hierarchy. We're just going to say hierarchy clustering, right? So the point is, though, is that instead of basically going from these kind of sets where you basically say, all right, initialize and try to find this distance, hierarchy clustering is kind of nice because you can kind of say, all right, let's start small and build up on top of it. And especially the agglomerative, like, I can't do it. All right, agglo, I'm going to pronounce it like that. Agglo clustering, right? Will specifically be useful when we do, when we want to visualize. I think it's a really cool way to visualize, but also allows us to do clusters within clusters. So I'm going to show, let's see here. So this right here is kind of showing like the clustering kind of the process. Excuse me. And so basically it starts, instead of trying to find like, you find the centroids and move outward, essentially the agglo basically allows you to, what's it called? You don't have to know how many clusters you need to begin with. You can basically run the algorithm without knowing ahead of time. And so what it does, it basically just pairs up points that are really close together. So the first initial points basically says, which 2 points are really, really close together, the closest together. And say, okay, like let's say like A and B or something, or let's say B and C right here are really close together. And then like, okay, E and F are really close together. I and H and J and K, basically groups those two that are very, very close together. Then once it goes through there, it's like, okay, what about, point G? It's like, well, point G, or let's say, that's not the right way. Now let's say like the next 2 closest points. So in this case, we might have, for example, like this is point B and point A. So we already labeled B and C together, but it's like, hey, B and A are really close together. Those are probably a group. So it actually add another cluster within that, saying, okay, well, B and C are a group. Excuse me. B and C are a group, but A is also, A should also be close to B. So A, B, C are a group, even though B and C are probably a better group. So you can kind of have this hierarchy of like making clusters within clusters within clusters. And then it'll go from there and say, okay, well, D is really close to E. So we'll include this as one big cluster here. And then same thing for I, H, and J, K. Say, oh, well, I and J are really close together and K are really close together. Okay, that really should be one big group here. And then we can start adding extra points and going further and further and further. And what's kind of cool is that we can see this 2-dimensionally, which is nice. But of course, most data sets are not 2 dimensions. Most aren't even 3 dimensions, and 3 dimensions is already hard enough. So most are really high dimensions. So it's nice that this algorithm also allows us to do something called a dendrogram. And a dendrogram basically allows us to kind of do this visualization without having to actually look at what the data set. So this dendrogram basically shows like, oh, J and K are really close together, I and H are really close together, but these groups together are really close. So they should be one group. And you can see every time we have these different branches, basically it makes a new group. Okay, so you can see here, like overall, this is like the biggest group, right? Which is all of them. And you can say, oh, there's like 2 main groups here, G, J, K, I, H, right, from this part. And then there's the rest of them on this part. And you can see that's this grouping here, this grouping here. And you can see there's smaller groups at the very beginning right here. And you can kind of go through. So what's nice about this is, again, like this works for any general dimensional data set. You can basically see the connections from here. So it's a great way to visualize, say like, oh, you can kind of see where clusters actually occur. And then what you say, like, well, okay, what if I want specific, what's it called? I want specifically 2 groups. Well, what you do, you basically just start from the very top and you basically say, all right, let me go ahead and get rid of this grouping right here. And whatever groups are left, in this case, there's 2 groups. And then you get, it's like, well, I don't want 2 groups, I want 3 groups. Like, well, okay, let's go ahead and cut off like the next part right here. It's like, okay, this is the next tallest one. And you can see, okay, now I have this group here, and this group here. So basically, as you want more and more clusters, you just keep working your way down, cutting off, saying, okay, well, everything now, instead of grouping them together, we're just going to make it separate. And you basically can keep working your way down to however many clusters you want. You can make it so the clusters are equal to the number of points. In that case, it would cut all the different pairings it had. Okay, so again, this is nice because it's a hierarchy structure. So it kind of gives you some extra structure in there. It lets you, what's it called? It lets you visualize it, which I think is a huge part with the dendrogram, because a lot of data is just not 2-dimensional or even 3-dimensional. So it allows you to kind of do this without having to sacrifice dimensionality or sacrifice information. And then it's kind of nice because it's the same, it's deterministic. So I don't have to worry about initializing my parameters like in that way. Basically, it's going to run the same hierarchy every single time. So I don't have to worry about saying, oh, did I initialize my centroid correctly? There are no centroids here. So I can just essentially say, okay, well, I just want the different thing. So if I could run this once and say, well, you know what? I want 5 clusters. Well, I can just cut those off. I don't have to run the whole algorithm to match them all up. Okay. So one way we can do this. You guys have any questions about this, like how this works? Mm-hmm.
So just so I'm clear, it's in that picture of the tree,
mm-hmm.
It starts at the bottom of the tree, right?
That's right.
Okay.
Yeah. So like the first pairing might be, for example, E and F, because E and F are the closest ones together. So I paired those ones first, and then you would then have the CB. So like eventually those trees would be drawn out as you went up. But usually at the end of the algorithm, you essentially have this whole tree, and then you would kind of cut off parts, basically group them together. Okay, cool.
We haven't really gotten to the coding of this, but is there a reason why we wouldn't just use the hierarchical clustering from the get-go?
Yeah.
Clustering
versus k-means, right?
Yeah.
Yeah. One issue with algo is that it really likes to use these it tends to go towards these elongated parts. It kind of reaches out, like this is the way I kind of think of it. It kind of reaches out and tries to grab like the closest thing that's near it. And you'll tend to get these like elongated parts. There's some ways we can do this, and we'll talk about it in types. But basically, like the simplest one is called single link. And if you it's actually not even scikit-learn. That's how like bad it is. But the first initial part, it can cause these slightly elongated parts, and it can be kind of a disadvantage in the sense that like, well, our data is not really supposed to be that way. So you instead of getting like these circular clusters that you would get in k-means, you might have more like these kind of longer curves, which are great when you have something that actually looks like this and things like this, but it might not be exactly what you want. And we'll talk about some ways you can alleviate that. So the first thing I kind of glazed over is how do I determine how far these points are. And the simplest one is single link. So when I have this grouping, like let's say E and 8F right here, say, okay, well, and I look at D, well, D and E are close together. So I would use like, okay, like single link basically says use the closest in this cluster to connect them together. So E and F should connect together with D, and you use E to determine that. Okay, and so for I, H, and J, K, those are 2 separate clusters, and say, well, okay, I want to see how these 2 clusters connect together. You would compare the 2 closest ones, I and J. This actually turns out to be really poor. Like basically you use the closest points and use that distance between them. And the reason why is because it tends, like I said, tends to create these elongated clusters and kind of tends to reach out to other points, and it starts grabbing points that are not probably part of it. So this ends to actually be really, really, like most people don't use single link because it's just not very good. And I think like it's not even scikit-learn. Like you can only do complete link, average link, ward link, or just ward. I don't think the curriculum even talks about single link, but just know that's the initial kind of like what you would probably think, like, oh, use the closest point to kind of determine it. Complete link basically is similar to single link, but instead it uses the farthest point. So it's kind of counterintuitive, but for connecting D and F, or this cluster, you would use F and D, the farthest point away from D. And then for combining IH and JK together, you'd use the farthest point in this cluster, which is H, from this point, K, and say, okay, are those closer versus, you know, G? And that kind of creates the different hierarchy. And that's how you kind of compare these parts. And what's nice is that it tends to create more compact clusters. However, it tends to ignore points that are really similar to the actual cluster. So the problem is let's see how can you do this. So one thing it can happen is that, like, let's say you have like your points right here, and then you have like another point right here. Okay. The problem is that this point right here is going to determine how far this one is over here, like if that belongs to the cluster. But this might not actually, like, let's say we combine these ones together and then we combined this one together, for example. It's not exactly how the algorithm will work, but something similar to this. The problem is that to determine that this whole cluster belongs, it will start using this point here. And the problem is that now you have something, it really shouldn't belong to this cluster, but instead, because it's so far back, it's basically picking out points that are further away from it. So this can kind of cause some issues in the sense of like, you might get some classifications like, well, it doesn't really belong to this group. It should really belong to this group, but it tends to kind of grab it on the other end because it's so far back. It's considered like, oh, that's the point that we're going to use to determine everything. This is not a good example because this is not actually what the algorithm would not come up with this thing, but I kind of want to show you like, oh, it kind of grabs these extra points in the back, on all that stuff. So this leads us to another part, and these things are like, it's like, oh, well, clearly this one's better than the next one or something like that. They're just dependent on the data set. If you know what the data set's going to look like, you might adjust which one you use. Average length, which you can probably guess, you basically just take the average of each point in the cluster and you compare those averages. So I would average I and H for their location and J and K their location and compare those two and do that from point to point. The last one is Ward, which is definitely the more complicated one. Like I think single link, complete link, and average link. Like you can think complete link also is like maximum. You can think of those like probably like those would be typically what you do is like, oh, I'd either pick the one that's closest to it or I'd pick the one that's farthest away, which might not be super intuitive, but it ends up being better for clustering, creating more compact clusters. Or you might do average, right? But Ward is kind of a weird one. Ward is actually the default for scikit-learn, for sklearn's clustering. And it basically does this thing, tries to minimize the variance during the cluster merge. So when it merges stuff together, it's trying to minimize that variance, basically how it changes. And the way we measure this, basically, it's kind of complicated. So I'm gonna walk through a little bit. If you imagine you have like cluster A, this is cluster A right here, and you have like cluster B, there's a few points that we can kind of like write out. There's the center between the two of them, okay? And I'm just gonna call it C0. And then the center between all the A points. So like if I averaged up all the A points, this would be like CA. And then the center of B would be like CB, okay? So these are different parts. And what we do, basically, we essentially find what the center is between the two clusters. Basically, you average up all of these points and say what's between, like, what's the average of all the points of A and B, and say what's the average of A and what's the average of B, okay? And then you have the CA, CB, C. Wow, really bad. So you probably can't tell which one's which, but you guys get the point. Square distance. So we square everything. So that's kind of like how we make sure it's like not positive, negative, and basically, all right, how far is each point of A to C? How far is each point of B to C? And we add that up. So this is the sum of all the XAs in A and all the XBs in B. Okay, these are all the XAs, these are all the XBs. And you basically sum those parts and square them. So this is the distance from like that center point, that C0. Okay, and then we do the same thing. We subtract off the distance from point A's to that's the center of A, and point B to the center of B's. Okay, so you kind of have like essentially like three big parts here. Okay, and you basically sum this all together, and basically we want to minimize this value. I maybe shouldn't write distance, but basically I think, yeah, I don't know. I'm trying to remember what I've seen before. I think I've seen like the difference, but essentially it's the distance. It's like our distance is variance. And you can see the variance kind of similar in the sense that we have, oh, we're just adding up squared terms, okay? And so we're trying to basically minimize this part. And so it's like, okay, this whole thing, after I do this whole calculation, that is the distance, quote unquote, from A to B. If I had like a group C over here, I would compare, you know, and I'm trying to combine A and B or B and C. I'm sorry, like A and C or B or C. You would compare those parts, and that would have a different distance from A to C or B to C. And that's kind of how we determine. And it turns out Ward's pretty good. I think actually if you look at, if you look at what's on scikit-learn here, the default, where is it? Right here. It does a pretty decent job. So you can see it here, and that's using Ward. And you can see there's some slight differences here that might not make sense. But for the most part, it does an all right job for doing that cluster. I'm sorry, I did. No, it's Aglo. Okay, yeah. So this actually does a decent job for most things. Depending on the data set, like you can see here, these elongated arms. I still had an issue with it, but this might be able to adjust it with parameters and such. Okay. So those are the different parts. Mostly, you'll probably use Ward just because it's the default. Any questions on how this, like, works in general. I don't think it's necessarily a difficult thing to understand, like how it works, but maybe it's just about the different distances. Yeah.
I have a question about, so if it's in 2 dimensions, Euclidean distance might make sense as a measure of distance between 2 points, but if it were in 3 dimensions, would it use a different kind of distance, like cosine distance or something?
You can possibly, but you can use Euclidean distance still in 3 dimensions because it's still just a line. So it would be like, use basically good old Pythagorean theorem, but extended. So if you imagine like, you just take the distance would be equal to the square root of the difference in x squared plus the difference in y squared, right? So like in the x direction, in the y direction, and then in the z direction. And then if you extend this out to like 4 dimensions plus like w squared and so on. So basically the distance would be the same, like the calculation at least. You could use cosine distance, but I believe single link, complete link, average link. I mean, look, if you look at this right here, this essentially is just using the distance like you would think in like Euclidean geometry. But yeah, that's what we mean by this minus term. Basically like subtract all those points, like how you normally would figure out the distance. Okay, cool, good question though. All right, so I'll show you some quick example code. So it's not too, like you can see it's actually pretty easy. Like this just imports. I use SciPy because I can't do dendrograms in scikit-learn, unfortunately, or sklearn. It's just not a thing that you can do, unfortunately. So I have some workarounds, but I'll just show you the actual implementing this algorithm. This is just getting the data. So it's the iris data. I'm just getting 30 different points. And you can see here, this is declaring it, saying, okay, I want 3 clusters, but I could have easily put like a different number of clusters. Do the fit, and then that's your model right there. Oh wait, I didn't even need this part. I don't know, I repeated it twice, but basically does the same exact thing. Like this is all of the code to basically make your clustering algorithm, which I mean, like you can see is pretty straightforward. I mean, obviously there's some extra parameters here too that you can kind of mess around with and kind of see like what exactly you want. But for the most part, that's kind of all it is to it. And then you have your model. So now you can actually use that model to fit in new points and get the points, just like you would do for any other machine learning algorithm. Now, if you wanted this nice, cool dendrogram, which could be super useful to see like what the clustering actually looks like, unfortunately, scikit-learn does not have this built in. You have to, most people end up using some form, like using SciPy, which is part of scikit-learn, but like it's not built in. So here I have, I want to see, oh no. So, okay, yeah, I'm using basically the model that I defined up here, which will make sure I run that. The model that I have here, I'm using that model and basically just doing some fancy footwork to allow it. I actually got this from Stack Overflow that someone had wrote, but it's a pretty nice, like, quick thing that they have here. Basically, it's just converting the stuff into a linkage matrix that SciPy needs to have in order to make these nice dendrograms right here. But this kind of allows you to kind of quickly look at, see like what points are close together and stuff like that. One thing I don't like about this particular set of code is that it's kind of hard to tell exactly like the coloring. You probably could adjust this code to make it so the coloring is equal to what's actually classified. But on the bottom here is at least this 0, 2s, and 1. So those are the 3 different classes. And you can kind of see, okay, I got more or less this peak over here, more or less a peak over here, more or less a peak over here. So you can kind of hopefully get an idea of what the hierarchy structure is going to look like. Starting different right here. This one's actually using scikit-learn directly. So this ward right here actually comes from importing here from scikit-learn, or sorry, not scikit-learn, SciPy. And basically it's doing the same algorithm, but it's using SciPy, which I don't know the exact like workings of SciPy versus scikit-learn's hierarchy implementation. So there might be some differences in that sense that you would want to be careful with. But what's nice is that it returns a link matrix. With this link matrix, I can actually create this dendrogram, which looks really nice. And you can kind of quickly see there's 2 big clusters right here. And you can probably see this, in my opinion, this is a little easier to see too versus this implementation, is you can see like, okay, even though it identified 3 clusters, you can kind of, or 2 clusters, you can kind of see there's almost like 3 here. There's one big cluster right here, a big cluster right here, and then maybe one right here. This could possibly be connected, but it seems like these are pretty close together. So you can kind of see these general shapes and stuff like that. But that might be helpful. Sorry, now all I can see like city skyline, but basically you can start getting this structure right here. And if you wanted like, 3 structures, you would get rid of, if I wanted 3 clusters, I would get rid of this, right? And that'd give me 2. and 1, 3, go like this, and you can see this would be my 1, my 2, and my 3 clusters. Okay.
What is the y-axis on that?
On this part right here, you know, I gotta be honest, I don't quite know. It might, to be honest, it might just be just so for it to draw it out. I'm sure if you went to the documentation of like Ward itself or of dendrogram, it probably would tell you more about like what exactly this is. Yeah, I'd have to dig into that exactly of what that axis actually means, but.
Yeah, okay, because it would be helpful if it could tell you like how many clusters there were at that layer, but it would be inverted from the values that it has.
Right, I wonder, no, yeah, I thought something, but it's not. Okay, yeah, I'm not quite sure exactly what those things are. If you dig into documentation, I'm sure you can figure out what it is and what it means. Okay, so this is everything that's on the curriculum for clustering. But I did want to show one last one that is not mentioned in the curriculum, but I think it's a useful one. It's called DBSCAN. And DBSCAN, I'm going to go through this relatively quickly. But DBSCAN basically is a similar algorithm, but instead what you do, you basically choose a point and you say, all right, you choose a random point and you say, all right, you defined already epsilon, which is kind of like your minimum distance, and your minimum sample is basically how many points have to be within a group in order to call it a group. So if you imagine like you had a bunch of data where you have like a bunch of data points and then like one over here, and you put in like certain algorithms, it might define this one point as a separate group, which doesn't really make sense. Like this point really should be noise. And so if you know your data is going to have a lot of noise in it, it might make sense to use this algorithm. So the first thing we define basically is epsilon, basically how far should the points be from each other before we call it a group? And then what's the minimum number of samples to call it a group? So what we do, we choose a point. We say, hey, are these points around it? Are there any points within epsilon around it? And if there are points, does it fit the minimum sample? And if it is, if we have a point and then within epsilon, like a kind of a circle around it, if there's like, let's say the minimum points is like 4, we say, okay, there's 4 samples around it. Cool, that means that is a core point. And then what we do, we look at the core point and say, all right, with everything around core points, then we go to the next. So we get a core point, and then we get to another data point. We look at that, and we check around it and say, okay, are there at least 4 minimum samples within epsilon? And you say, no. But it's like, okay, was there a core point within epsilon? And they're like, oh, yeah, it is. Then we call that a border point. So the idea here, you'll get basically a bunch of like, what's it called, core points. And then you'll get a few border points. And then if there's something that doesn't cross over with a core point or the minimum number of samples with an epsilon, we'll call that like noise. And that's basically the whole algorithm of DBSCAN. So this one, again, same website, but does a visualization. So I'll do Gaussian mixture again, and we'll say epsilon of 1, minimum of 4 points. And basically what it's going to do is just going to go around each point and look around and say, all right, what are core points, I believe? Yeah. So basically it's just looking around and say, all right, what things for each point going around, figuring out if things are going to be close together or not. So you can see here is that that's what that little blue circles are going on right now, is that it's going around each point and seeing what's near it, if there are points or not. And you can see there's a few of them on the outside, like these guys. These are noise points. Basically, these ones don't have anything near it, okay? And what's nice is that you don't have to actually know how many groups there are. It can figure this out for you. So, and again, you can see this noise right here. If I want to restart it with the same data, let's do a Gaussian mixture again. I think it's the same data. And let's say I increase epsilon. So you can see basically how close points have to be. Let's say, oh, points have to be really close together in order for me to count in a group. And I'll say a minimum of like, let's say just keep it at 4. So we can see here, our little epsilon is going to be much smaller. So points have to be really close together in order for me to call it a group. And then you can see like, he's like, okay, like, but it has to have at least 4 points. So most of this is noise, for example. I say, okay, they have to be really close together and there has to be a lot of them close together. And you can see they identified new data points and stuff like this. So you kind of get the idea here, is if we can adjust this. I want to show uniform points. So this one's like supposed to be random, basically, okay? And if I do this right here, if we're lucky, we might find that most of these are basically just one big group. So you can kind of have it keep going through. I might have to adjust this to basically account for more points for its minimum number. but you can see because it's kind of spread out what's going on. But as we kind of let this go further and further in there, it'll actually start combining the groups together. Say, oh wait, these are actually together because they're more than just core points. So basically what ends up happening, let's just run for a second, but for example, for DBSCAN, it'll tend like a random uniform like this, create all one big group. And then you can see here is that if you have something like this, it might define these different, different noise points. And you could probably get a little bit better if you adjusted the parameters on this to make it like 3 different groups, closer to like what these 2 guys, like with Ward does. But you just kind of like have to decide what makes sense for you to be what makes sense to be a group. Does it have to be really close or should it be further out? So you can kind of see that wasn't the best because maybe I didn't have the same minimum points is at least like, I don't know, it's 5. And then epsilon, we'll be generous. And we can let it go and do all this stuff. So anyway, that's DBSCAN. And DBSCAN is pretty straightforward again. That's the whole code of DBSCAN. Obviously you have to import it, but like pretty straightforward. Basically you define your epsilon, your minimum samples. There's some other parameters here too, but those are your 2 main ones. You can see, for example, your metric, how you measure your distance. So for example, Euclidean versus something else, okay, and all that stuff. Cool. Any questions you guys have, whether it's DBSCAN or something else?
At the beginning of the lecture, you said that the 2 crescents like that are famous. What did you mean by that?
I meant it's one that's a classic one that will trip up a lot of algorithms because you can intuitively understand like, well, those should be 2 separate groups, but depending on the different algorithms, like you can see like these ones tend to do very badly. And that's why you can see like a lot of these algorithms tend to do really well on this one. It's because this was kind of considered like, oh, this is a group that could be really useful, but a lot of algorithms would get it wrong. So a lot of times it was tested to make sure this works out properly. Okay. Oh, I just forgot about this. You can actually see the timing here too. So you see how much time it takes for each algorithm to run these different parts. So you can see, for example, DBSCAN's pretty damn fast. 0.02, 0.01. Basically, it can work this in parallel because it doesn't have to worry about making a hierarchy versus a hierarchy here can take some time depending on what the structure looks like. Okay, cool. All right. Yep. So cool. Any other questions you guys have? All right. Awesome. All right. So I'll go ahead and stop it here.